Okay, this is the second of our videos on vector differentiation and coordinate systems, and here we will explore plane polar coordinates. Now, here we're just working in 2D, but this is a useful coordinate system for many things. For instance, looking at orbital mechanics, you can show that an orbit, a typical orbit, will lie in a plane. So if we set our coordinate system to occupy that plane, it makes things a lot simpler. So we have to remember, though, that all of our differentiation is defined in terms of Cartesian coordinates. So I'm still going to have to put in a Cartesian coordinate system, and I will note the unit vectors I hat and j hat. Okay, so let's say we've got some object located here, and we can express its position by a vector r. Now, in plane polar coordinates, what we do is we make our coordinate system actually follow the object in question. So what this means is that our unit vectors at the moment, our hat points straight away from the center along the position of our object, and then our angle off the x-axis, theta, well, since we go counterclockwise to measure angle, we'll say that our theta hat is at right angles, going in a counterclockwise-y kind of way, again, at that point. So now, if I were somewhere else, let's say here, just by sake of argument, then at this point, my r hat would be pointing away like that, and my theta hat would be pointing counterclockwise-y around that point. This does lead to something kind of counterintuitive, and that is that our position r is equal to r, our r coordinate, times r hat, and that's it. And this is because this uniquely identifies the position, believe it or not, because our r hat is a function of theta. If we were somewhere else, our r hat would point somewhere else. So this may be a little weird to wrap your head around, but it's okay. And it sure makes calculating things a lot more convenient. But there is a cost. Let's say I want to find the velocity. Well, that will be r dot. That's all well and good. But now we got to think about what that means. I am differentiating with respect to time r hat. Now, r hat is not a constant. As the object moves, r hat will point somewhere else. So this means I have to write it as r dot r hat, and then I have to follow through with my chain rule and say that this is equal to r hat dot. Okay, so if our r is changing with respect to time, so here's my r hat, theta hat points at an angle. Sorry, that should have been r hat right there. At some later time, my r and r hat won't point those same places. My r hat will have ended up over there, and my theta hat will have ended up over there. And in both cases, here and here, we will have churned through by some angle delta theta. Now, if we let our time interval approach 0, so as delta t goes to 0, delta theta will also go to 0. And so what that will mean is that my delta theta will be perpendicular to theta hat, and my delta r hat will be perpendicular to r hat itself as well. Okay. So now if r, just the magnitude r changes, nothing happens. It just translates the unit vectors, but it doesn't change their direction, so we're still good there. Okay. So what we get out of this is that my r hat dot, or that's dr hat dt, that will be equal to theta dot theta hat. And similarly, theta hat dot will be equal to minus theta dot r hat. See, this is my negative r hat direction, so we're perpendicular that way. This is in the theta hat direction, so we're perpendicular that way. And the rate of change is equal to theta dot. So when I differentiate, so going back to my velocity here, we said that that was equal to r dot. Okay, that's all good. R hat, that's fine, plus r, but we've just worked out that r hat dot is theta dot theta hat. Okay, that's probably the preferred way to try to think about these things. But if that's getting a little painful for you, there are other ways, but they kind of involve gutting things out. You can always get away with going to Cartesian coordinates, doing your derivatives in Cartesian coordinates where they're defined, and then transforming back out. Here's what I mean by that. So in this example here, we'd say that r, we can write that as in Cartesian coordinates as r cosine theta I hat plus r sine theta j hat. Now you see that's more complicated than just writing r hat, but I hat and j hat don't move on you, so pick which one you like. Okay, so my velocity is going to be equal to r dot, so now I need to differentiate this with respect to time. So now ddt of I hat is the null vector, so we're good there. We just have to worry about the two terms we'll get differentiating this product here. So we'll pick up an r dot cosine theta, and then I will have an r, now the derivative of cosine is minus the sine of theta, and I'll pick up a theta dot I hat. Then looking at this term, we'll get plus, we'll have an r dot sine theta plus r, derivative of sine is cosine theta, derivative of what's inside is theta dot j hat. Okay. Now, what we can do is we can look at these r's here, and we can realize that my r hat would have to be equal to cosine theta I hat plus sine theta j hat. We can go back and take a look here. You can see here that the x component here would be r cosine theta, the y component there would be r sine theta. By the same token, you can convince yourself that theta hat would have to be equal to minus sine theta I hat plus cosine theta j hat. So if we're clever about this, we recognize, hey, this r dot here will have a cosine theta I hat, sine theta j hat. So let's go and follow this from here. So my r dot is equal to, pulling out an r dot part here, we'll have a cosine theta I hat plus sine theta j hat. And we still have the terms here with r, so we'll pull out the r. And well, you know, oh, and we got a theta dot, we can pull that out. So r theta dot. And now we're left with minus sine theta I hat plus cos theta j hat. Excellent. So if I look at this, I recognize that this much here is r hat, and that much there is theta hat. So now I can go back into polar coordinates and write that rv equals r dot equals r dot r hat plus r theta dot theta hat, which is what we had before. Now I kind of consider this a last resort approach. I think it's a lot easier to try to think about how the unit vectors have to rotate around. But until you get used to doing that, this is a good way to check your work. Okay, fortunately, we don't really have to do anything new for finding the acceleration. So for the acceleration, that's v dot, or we could write that as r double dot, just to get you used to the notation. So this will be the time derivative of the v that we just found right here. So we'll put that in. So we're going to differentiate r dot r hat plus r theta dot theta hat. Okay, so this first bit here will give me second derivative, so we'll have an r double dot r hat plus we'll have an r dot r hat dot. And then we'll pick up three terms from here. We'll get an r dot theta hat plus an r theta double dot theta hat plus an r theta dot theta hat dot. Okay, and again we make the same kind of substitutions that we made before. Remember that we worked out, here that r hat dot is theta dot theta hat, and that theta hat dot is minus theta dot r hat. So we'll substitute those in where we see them. So this will be equal to r double dot theta hat. Oops, my bad. Try that again. This will be r double dot r hat plus, again, I have myself r dot theta hat plus r dot theta hat plus r theta double dot theta hat plus r theta minus theta dot r hat. Okay. So if we group them together, we've got two things with r hats. So we'll have an r double dot from here, and then from here we'll have a minus r theta dot squared r hat. Right. Oops, yeah, I forgot the theta dot right there and there. Okay. And then grouping the theta hats here, this will be plus, well, we'll have an r theta double dot, and we picked up two terms of r dot theta dot times theta hat. So that's our acceleration in plane polar coordinates. Okay, I think it's certainly worth doing an example here at this point, just to get a flavor for how this goes and to try to interpret it a bit. So let's look at spiral motion. Okay, so one way we can do a spiral, or parameterize a spiral, is to say that r is equal to some b times t, and theta is equal to omega t. Now let's find the velocity and acceleration vectors. Okay, so following our prescription, said that the velocity vector will be equal to r dot r hat plus r theta dot theta hat. All right. Well, if we look at this here, r dot is equal to b, theta dot will be equal to omega. So we get that this is equal to b r hat plus r omega t, sorry, b omega t, b omega t theta hat. Okay, so that's the velocity. If we wanted the speed, just throwing in a little extra here, the speed v would be equal to the square root of v dot v. So that's the square root of b squared plus b squared omega squared t squared. Alrighty. Alright, so now we can go ahead and look at finding the acceleration. So that's a little uglier. That's going to be r double dot minus r theta dot squared r hat plus r theta double dot plus 2r dot theta hat. But thankfully here b is a constant, so r double dot is 0, omega is a constant, so theta double dot is 0. So we'll take it where we get it. So that means that term goes to 0, and that term goes to 0. Yes. So we end up with, okay, my r, we said was equal to bt, so it's be minus b, theta dot is omega squared t, r hat, that looks bad, r hat plus 2, r dot is just b, theta dot is just omega, theta hat. Okay, and these pieces here have names. We usually call this the radial or the centripetal acceleration, and this is the tangential. And remember from before, this is the bit that's responsible for changing the direction. That's the bit that's responsible for changing the speed. So if we think about this a little further, it does seem a little weird. You know, as our radius is increasing, it may not seem intuitive at first blush that our radial acceleration should also be increasing as a function of time. The tangential bit stays the same, but you can see the radial bit is increasing. But let's work that out using some physics 243. We go back and just say, well, AC is v squared over v tangential squared over r. Well, my v tangential here is b is equal to b omega t, right? So this would be b squared omega squared t squared, and my r is equal to bt. Okay, we lose 1 power of t, 1 power of b, And so what we see is that the tangential velocity, the tangential speed is increasing linearly with time as well, but since its influence to the radial acceleration goes as the square, even though the radius is only increasing as the time, that still leaves us 1 power of the time. And so as we continue our ever faster spiral, it turns out that the required centripetal acceleration will keep going up. Okay, that concludes part 2 of these videos. The third and last part will be taking a look at the 3D systems of cylindrical and spherical coordinates.